Galvanic corrosion damage mechanisms is a part of uniform or localized loss of thickness. Description of galvanic corrosion damage mechanisms based on API 571, a form of corrosion that can occur at the junction of dissimilar metals when they are joined together in a suitable electrolyte, such as a moist or aqueous environment, or soils containing moisture. Starting by understanding the definition of galvanic corrosion. Number 1 is electrolyte. A substance that contains free ions and can conduct electricity. In the context of galvanic corrosion, an electrolyte is typically a liquid, such as seawater or an acidic solution, that facilitates the flow of ions between the anode and cathode, enabling the electrochemical reaction. Number 2 is anode. The electrode where oxidation occurs in an electrochemical cell. In galvanic corrosion, the anode is the metal that loses electrons and corrodes. It is the more reactive metal in the galvanic pair. Number 3 is cathode. The electrode where reduction occurs in an electrochemical cell. In galvanic corrosion, the cathode is the metal that gains electrons and is protected from corrosion. It is the less reactive metal in the galvanic pair. Number 4 is catalyst. A substance that increases the rate of a chemical reaction without being consumed in the process. Catalysts are not directly involved in galvanic corrosion but are crucial in many other chemical reactions, including industrial processes and biological systems. What is galvanic corrosion? Galvanic corrosion is an electrochemical process that occurs when two different metals come into electrical contact within a corrosive environment, such as water containing salts or acids, the electrolyte. This contact creates a galvanic cell, leading to one metal, the anode, corroding faster than it would on its own, while the other metal, the cathode, corrodes more slowly or not at all. Key components of galvanic corrosion damage mechanisms. Number 1 is dissimilar metals. Metals with different electrochemical potentials. Common pairs include steel and copper, aluminum and stainless steel, etc. Number 2 is electrical contact. Direct physical contact or connection through a conductive medium. Number 3 is electrolyte. A conductive solution that facilitates the flow of ions, such as seawater, rainwater, or even moist air. How galvanic corrosion damage mechanisms works. Number 1 is electrochemical reaction. When the metals are in contact, electrons flow from the anode, the more reactive metal, to the cathode, the less reactive metal. Number 2 is anode corrosion. The anode loses electrons and undergoes oxidation, leading to corrosion. Number 3 is cathode protection. The cathode gains electrons and is protected from corrosion. Example of galvanic corrosion damage mechanisms works. Imagine a steel bolt, anode, used to connect a copper plate, cathode, in a marine environment. The steel bolt will corrode faster due to the galvanic reaction, while the copper plate remains relatively unaffected. Galvanic corrosion damage mechanisms affected materials based on API 571. All metals with the exception of most noble metals. What are noble metals? Noble metals are a group of metals that are highly resistant to corrosion and oxidation in moist air. They are often found in their pure, metallic form in nature due to their low reactivity. Here are some key characteristics and examples of noble metals. Number 1 is characteristics of noble metals, includes. Number A, of characteristics of noble metals is corrosion resistance. Noble metals do not easily corrode or tarnish, making them ideal for use in environments where other metals might degrade. Number B, of characteristics of noble metals is chemical stability. They are chemically inert and do not react easily with other elements or compounds. Number C, of characteristics of noble metals is high electrical conductivity. Many noble metals are excellent conductors of electricity. Number D, of characteristics of noble metals is luster and malleability. They have a shiny appearance and can be easily shaped or molded. Let's talk about the number 2 is about common noble metals. Number A, of common noble metals is gold. Gold known for its luster, malleability, and resistance to tarnish. Widely used in jewelry, electronics, and as a monetary standard. Number B, of common noble metals is silver. Silver is a highly conductive and used in jewelry, electronics, and photography. Number C, of common noble metals is platinum. Platinum is a resistant to corrosion and used in catalytic converters, jewelry, and medical devices. Number D, of common noble metals is palladium. It used in electronics, dentistry, and catalytic converters. Number E, of common noble metals is rhodium. It is extremely resistant to corrosion and used in catalytic converters and as a plating material for jewelry. Number F, of common noble metals is iridium. It is highly resistant to corrosion and used in high-temperature applications and electrical contacts. Number G, of common noble metals is ruthenium. It is used in electronics and as a catalyst in chemical reactions. Applications of noble metals. Number A, of noble metals application is jewelry. Due to their luster and resistance to tarnish, noble metals are popular in making fine jewelry. Number B, of noble metals application is electronics. Their excellent conductivity makes them valuable in electronic components. Number C, of noble metals application is catalysis. Noble metals like platinum and palladium are used as catalysts in various chemical reactions, including in automotive catalytic converters. Understanding galvanic series. The galvanic series, also known as the electropotential series, is a list that ranks metals and alloys based on their electrochemical reactivity in a specific environment, typically an electrolyte like seawater. This series helps predict and understand galvanic corrosion by showing which metals are more likely to corrode when paired with others. Number 1 of understanding galvanic series is to know the key points of the galvanic series, includes. Number A, of key points of the galvanic series is order of nobility. Metals are arranged from the most noble, least likely to corrode, to the least noble, most likely to corrode. Noble metals, like gold and platinum, are at the top, while active metals, like magnesium and zinc, are at the bottom. Number B, of key points of the galvanic series is electrochemical potential. The position of a metal in the series is determined by its electrode potential. Metals with higher, more positive, potentials are more noble, while those with lower, more negative, potentials are less noble. Number C, of key points of the galvanic series is galvanic couples. When two metals from different positions in the series are in electrical contact within an electrolyte, the metal lower in the series, anode, will corrode, protecting the metal higher in the series, cathode. Number 2 of the understanding of galvanic series is to know several examples of the galvanic series in seawater. Most noble metals, or least reactive, of the galvanic series in seawater are the following: gold, platinum, silver, titanium, stainless steel, passive. Intermediate metals in the galvanic series in seawater are the following: copper, brass, bronze, nickel, tin. Least noble metals, or most reactive, in the galvanic series in seawater are the following: steel, aluminum, zinc, magnesium. Number 3 of understanding galvanic series is to know the practical use. Number A, of practical use of galvanic series is material selection. Engineers use the galvanic series to select compatible metals for construction, especially in corrosive environments. Number B, of practical use of galvanic series is corrosion prevention. By choosing metals close to each other in the series, the risk of galvanic corrosion can be minimized. Alternatively, protective measures like coatings or sacrificial anodes can be used. Galvanic corrosion can affect a wide range of materials, particularly when they are paired with dissimilar metals in the presence of an electrolyte. Here are some common materials that are susceptible to galvanic corrosion, includes. Number 1. Commonly affected materials. Number A, of commonly affected materials is steel and iron. Often corrode when in contact with more noble metals like copper or stainless steel. Number B, of commonly affected materials is aluminum. Highly susceptible when paired with copper or brass. Number C, of commonly affected materials is zinc. Commonly used as a sacrificial anode to protect other metals, but corrodes rapidly when in contact with more noble metals. Number D, of commonly affected materials is magnesium. Extremely reactive and corrodes quickly when in contact with almost any other metal. Number E, of commonly affected materials is copper and copper alloys. Can cause galvanic corrosion in metals like steel, aluminum, and zinc. Number 2 is common metal pairs. Number A, of common metal pairs is steel and copper. Steel will corrode faster when in contact with copper. Example for steel and copper is plumbing systems where copper pipes are connected to steel fittings. The risk for steel and copper is: steel as anode corrodes faster when in contact with copper as cathode. Number B, of common metal pairs is aluminum and stainless steel. Aluminum will corrode when in contact with stainless steel. Example for aluminum and stainless steel is aircraft construction where aluminum components are fastened with stainless steel bolts. The risk of using aluminum and stainless steel is aluminum as anode corrodes when in contact with stainless steel as cathode. Number C, of common metal pairs is zinc and steel. Zinc will corrode to protect iron in galvanized steel. Example for zinc and steel is galvanized steel, where a zinc coating is applied to steel to protect it. The risk for using zinc and steel is: zinc as anode corrodes to protect the underlying steel as cathode. Number D, of common metal pairs is magnesium and aluminum. Example of magnesium and aluminum is automotive parts where magnesium components are used with aluminum parts. The risk of using magnesium and aluminum is: magnesium, anode, corrodes rapidly when in contact with aluminum, cathode. Number E, of common metal pairs is brass and steel. Example of using brass and steel is in marine environments where brass fittings are used with steel structures. The risk of using brass and steel: steel as anode corrodes faster when in contact with brass as cathode. Galvanic corrosion damage mechanisms critical factors based on API 571. Number A, for galvanic corrosion, 3 conditions must be met the following. Number 1 is presence of an electrolyte, a fluid that can conduct a current. Moisture or a separate water phase is usually required for the solution to have enough conductivity. Number 2 is 2 different materials or alloys known as the anode and the cathode, in contact with an electrolyte. Number 3 is an electrical connection must exist between the anode and the cathode. Number B, of galvanic corrosion damage mechanisms critical factors based on API 571 is the more noble material, or cathode, is protected by sacrificial corrosion of the more active material, or anode. The anode corrodes at a higher rate than it would if it were not connected to the cathode. Number C, of galvanic corrosion damage mechanisms critical factors based on API 571 is a typical listing of the relative position of alloys in seawater is shown in Table 4.6. Number D, of galvanic corrosion damage mechanisms critical factors based on API 571 is the farther the alloys are apart in the table, the higher the driving force for corrosion. Number E, of galvanic corrosion damage mechanisms critical factors based on API 571 is the relative exposed surface areas between anodic material and the cathodic material has a significant effect. Number 1 is corrosion rates of the anode can be high, if there is a small anode to cathode ratio. Number 2 is corrosion rates of the anode will be less affected if there is a large anode to cathode ratio. Number 3 is if there is a galvanic couple, the more noble material may need to be coated. If the active material were coated, a large cathode to anode area can accelerate corrosion of the anode at any breaks in the coating. Number 4 is the same alloy may act as both an anode and a cathode due to surface films, scale, and/or local environment, for example, old steel pipe connected to new steel pipe. Several critical factors influence the extent and rate of galvanic corrosion damage. Understanding these factors can help in preventing and mitigating the effects of galvanic corrosion. Critical factors of galvanic corrosion damage. Number 1 is electrochemical potential difference. The greater the difference in electrochemical potential between the two metals, the higher the rate of corrosion for the anode. Metals with a larger potential difference will experience more severe galvanic corrosion. Number 2 is presence of an electrolyte. An electrolyte, such as seawater, rainwater, or even moist air, is necessary to facilitate the electrochemical reactions. The conductivity and composition of the electrolyte can significantly impact the corrosion rate. Number 3 is electrical contact. Direct electrical contact between the dissimilar metals is essential for galvanic corrosion to occur. This contact allows the flow of electrons from the anode to the cathode. Number 4 is surface area ratio. The relative surface areas of the anode and cathode play a crucial role. A smaller anode surface area compared to the cathode will lead to a higher corrosion rate for the anode, as the electrochemical reactions are concentrated on a smaller area. Number 5 is environmental factors. Temperature, humidity, and pH levels can influence the rate of galvanic corrosion. Higher temperatures generally increase the reaction rates, while extreme pH levels can either accelerate or inhibit corrosion depending on the metals involved. Number 6 is metal pairing. The specific combination of metals used can determine the severity of galvanic corrosion. Metals that are far apart in the galvanic series are more likely to experience significant corrosion when paired together. Galvanic corrosion damage mechanisms affected units or equipment based on API 571. Number A is galvanic corrosion can occur in any unit where there is a conductive fluid and alloys are coupled. Heat exchangers are susceptible if the tube material is different from the tube sheet and/or baffles, particularly if saltwater cooling is utilized. Number B is buried pipelines. Electrical transmission support towers and ship hulls are typical locations for galvanic corrosion. Galvanic corrosion can affect a wide range of units and equipment, especially those involving dissimilar metals in contact within a corrosive environment. Here are some commonly affected units and equipment. Number 1 is marine vessels. Number A of marine vessels is hull and propellers. Steel hulls in contact with bronze or brass propellers can experience galvanic corrosion. The impact in between hull and propellers. The steel hull as anode corrodes faster due to the galvanic reaction, leading to material loss and potential structural failure. Number B of marine vessels is fasteners and fittings. Stainless steel fasteners used with aluminum structures can lead to corrosion of the aluminum. The impact in between fasteners and fittings is: aluminum as anode corrodes when in contact with stainless steel as cathode, compromising the integrity of the structure. Number 2 is piping systems. Number A of piping systems is water and gas pipelines. Copper pipes connected to steel fittings or valves can result in accelerated corrosion of the steel components. The impact in between water and gas pipelines. Steel as anode corrodes faster, leading to leaks and potential system failures. Number B of the piping systems is heat exchangers. Tubes made of different metals, such as copper and steel, can suffer from galvanic corrosion. The impact happens in heat exchangers is, the less noble metal, or anode, corrodes, reducing the efficiency and lifespan of the heat exchanger. Number 3 of affected units and equipment is electrical equipment. Number A of electrical equipment is connectors and terminals. Copper connectors used with aluminum wiring can lead to corrosion of the aluminum. The impact in between connectors and terminals is: aluminum, as anode, corrodes, leading to poor electrical connections and potential failures. Number B of electrical equipment is power distribution systems. Various metal components in contact within power distribution systems can be affected. The impact of power distribution systems is corrosion of the less noble metal can lead to electrical faults and reduced system reliability. Number 4 of the commonly affected units and equipment is automotive parts. Number A of automotive parts is engine components. Aluminum engine parts in contact with steel bolts can experience galvanic corrosion. The impact happens in engine components as aluminum as anode corrodes, potentially leading to engine damage and reduced performance. Number B, of automotive parts is body panels. Different metal panels and fasteners can lead to corrosion issues. The impact of body panels as corrosion issues can compromise the structural integrity and appearance of the vehicle. Number 5 of the commonly affected units and equipment is construction materials. Number A, of construction materials is roofing and cladding. Metal roofing sheets in contact with different metal fasteners can suffer from galvanic corrosion. The impact between roofing and cladding as galvanic corrosion can lead to leaks and structural damage. Number B, of construction materials is structural frames. Steel frames in contact with aluminum or copper components can lead to corrosion. The impact of structural frames as corrosion can weaken the structural integrity of buildings. Number 6 of commonly affected units and equipment is industrial equipment. Number A, of industrial equipment is chemical processing units. Equipment involving dissimilar metals in chemical plants can be prone to galvanic corrosion. The impact of chemical processing units as corrosion can lead to equipment failure and process inefficiencies. Number B, of industrial equipment is refinery equipment. Various metal components in refineries can experience corrosion due to the harsh environment. The impact of refinery equipment as corrosion due to harsh environments can compromise the safety and functionality of the equipment. Galvanic corrosion damage mechanisms appearance or morphology of damage based on API 571. Number A is, damage occurs where two materials are joined at welded or bolted connections. Number B, the more active material can suffer generalized loss in thickness or may have the appearance of a crevice, groove or pitting corrosion, depending on the driving force, conductivity and relative anodic/cathodic areas ratio. Number C, corrosion of the anode may be significantly higher immediately adjacent to the connection to the cathode, depending on solution conductivity. See Figure 4.70, preferential galvanic corrosion of the more active component of the two materials. See Figure 4.71, galvanic corrosion of a carbon steel nipple in a SS vessel in warm water service. The appearance or morphology of galvanic corrosion damage can vary depending on the metals involved, the environment, and the duration of exposure. Here are some common characteristics of the appearance or morphology of galvanic corrosion. Number 1 is pitting. Description of pitting. Small, localized pits or holes on the surface of the anode metal. Pitting is a localized form of corrosion that results in small, deep cavities or holes on the surface of the metal. It often occurs when the protective oxide layer on the metal breaks down, exposing the underlying metal to the corrosive environment. Pitting is particularly dangerous because it can penetrate deeply into the metal, compromising its structural integrity. Example: pitting on aluminum when in contact with stainless steel. Number 2 is rust and discoloration. Description of rust and discoloration is rust formation and discoloration, typically reddish-brown, on the anode metal. Rust refers to the reddish-brown flaky coating that forms on iron or iron alloys due to the reaction with oxygen and water. This process is specific to iron and its alloys. Discoloration can occur on various metals as a result of galvanic corrosion, leading to changes in color and appearance. For example, copper may develop a green patina, while aluminum may show white or grayish spots. Example: rust on steel when in contact with copper. Number 3 is material loss. Material loss description. Visible thinning or loss of material on the anode metal. Material loss involves the thinning or reduction of the metal's thickness due to corrosion. This can lead to weakened structures and potential failure. In galvanic corrosion, the anode metal experiences accelerated material loss as it undergoes oxidation and loses electrons. Example: thinning of zinc coatings on galvanized steel. Number 4 is cracking and fissures. Cracking and fissures description. Cracks or fissures that propagate through the metal, often following grain boundaries. Cracking and fissures are fine cracks or splits that can develop along grain boundaries in the metal. These are often the result of localized galvanic corrosion, where the anodic metal corrodes along its grain boundaries, leading to crack-like fissures. This type of damage can be difficult to detect and may lead to catastrophic failure if not addressed. Example: cracking in aluminum alloys when in contact with stainless steel. Number 5 is surface roughness. Surface roughness description: increased roughness and uneven surface texture on the anode metal. Surface roughness refers to the uneven texture that develops on the metal surface due to corrosion. Increased roughness can result from the localized attack on the anode metal, leading to a rough and pitted surface. This roughness can affect the metal's performance and aesthetic appearance. Example: roughened surface on magnesium when in contact with aluminum. General example: in marine environments, steel hulls in contact with bronze propellers often show pitting and rust formation on the steel, while the bronze remains relatively unaffected. This combination of damage types can severely compromise the integrity of the vessel. Galvanic corrosion prevention and mitigation based on API 571. Number A. The best method for prevention/mitigation is through good design. Number B. Differing alloys should not be in intimate contact in conductive environments unless the anode/cathode surface area ratio is favorable. Number C. Coatings can be helpful, but the more noble material should be coated. Number D. For piping, specially designed electric insulating bolt sleeves and gaskets can eliminate the electrical connection. Number E. Galvanic corrosion is the principle used in galvanized steel, where the ZN corrodes preferentially to protect the underlying carbon steel. If there is a break in the galvanized coating, a large anode to small cathode area prevents accelerated corrosion of the steel. This anode-to-cathode relationship reverses at water temperatures over about 150 degrees Fahrenheit, or 66 degrees Celsius. Preventing and mitigating galvanic corrosion involves several strategies aimed at minimizing the electrochemical reactions between dissimilar metals. Here are some effective methods of galvanic corrosion prevention and mitigation strategies. Strategy number 1 is material selection. Material selection involves choosing metals that are close to each other in the galvanic series to minimize the potential difference and reduce the risk of galvanic corrosion. For example, using metals like stainless steel and titanium together is preferable over pairing stainless steel with aluminum. This strategy helps in reducing the electrochemical potential difference, thereby minimizing the galvanic reaction. Choose compatible metals. Select metals with similar electrochemical potentials to reduce the potential difference and minimize galvanic corrosion. Galvanic series. Refer to the galvanic series to choose metals that are close to each other in the series. Galvanic corrosion prevention and mitigation strategies number 2 is insulation. Insulation is a method to prevent direct electrical contact between dissimilar metals. This can be achieved by using non-conductive materials such as rubber, plastic, or polymer-based bushings, washers, and gaskets. These materials act as barriers, blocking the flow of electrons and preventing the electrochemical reactions that cause corrosion. Non-conductive barriers. Use non-conductive materials, such as rubber or plastic, to separate dissimilar metals and prevent direct electrical contact. Gaskets and sleeves. Install insulating gaskets and sleeves in piping systems to isolate metals. Galvanic corrosion prevention and mitigation strategies number 3 is protective coatings. Protective coatings involve applying a layer of material to the metal surfaces to prevent exposure to the electrolyte. Common coatings include paints, anodizing, and sacrificial coatings like zinc plating. These coatings act as physical barriers, isolating the metals from the corrosive environment and reducing the risk of galvanic corrosion. Paints and platings. Apply protective coatings, such as paints, platings, or anodizing, to the metals to prevent exposure to the electrolyte. Barrier coatings. Use barrier coatings to physically separate the metals from the corrosive environment. Galvanic corrosion prevention and mitigation strategies number 4 is sacrificial anodes. Sacrificial anodes are more reactive metals that are intentionally used to protect less reactive metals. Common sacrificial anodes include zinc, magnesium, and aluminum. These anodes corrode preferentially, sacrificing themselves to protect the more valuable metal structures. This method is widely used in marine environments, pipelines, and storage tanks. Cathodic protection: use a more reactive metal, sacrificial anode, to protect the less reactive metal, cathode. The sacrificial anode corrodes instead of the protected meta. Common anodes: zinc, magnesium, and aluminum are commonly used as sacrificial anodes. Galvanic corrosion prevention and mitigation strategies. Number 5 is design considerations. Design considerations involve strategic planning during the design phase to avoid galvanic corrosion. This includes: Number A. Avoid dissimilar metal contact. Design systems to avoid direct contact between dissimilar metals whenever possible. Number B. Surface area ratio. Ensure the anode has a larger surface area compared to the cathode to reduce the corrosion rate. Number C. Proper drainage. Designing structures to avoid water accumulation, which can act as an electrolyte and promote corrosion. Galvanic corrosion prevention and mitigation strategies. Number 6 is environmental control. Environmental control focuses on managing the conditions that contribute to galvanic corrosion. This includes: Number A. Humidity control, using dehumidifiers or sealants to reduce moisture exposure. Number B. Temperature regulation, controlling the temperature to slow down the corrosion reactions. Number C. pH control, adjusting the pH levels of the environment to inhibit corrosion. Control electrolyte exposure, minimize exposure to corrosive environments by controlling humidity, using dehumidifiers, or applying sealants. Regular maintenance, perform regular inspections and maintenance to detect and address early signs of corrosion. Example: in marine environments, using zinc sacrificial anodes on steel hulls can effectively prevent galvanic corrosion. The zinc anodes corrode instead of the steel, protecting the hull from damage. By implementing these strategies, the risk of galvanic corrosion can be significantly reduced, ensuring the longevity and reliability of metal structures and components. Galvanic corrosion damage mechanisms inspection and monitoring based on API 571, visual inspection and UT thickness gauging are very effective methods for detecting galvanic corrosion. The damage may sometimes be hidden underneath a bolt or rivet head. Detecting and monitoring galvanic corrosion is crucial for maintaining the integrity and longevity of metal structures and components. Here are some common inspection and monitoring methods used to detect galvanic corrosion damage. The first is inspection methods, includes: Number 1 of common inspection methods is visual inspection. Description of visual inspection. Regular visual checks for signs of corrosion, such as pitting, rust, discoloration, and material loss. This is the simplest and most common method, involving a thorough visual examination of metal surfaces for signs of corrosion, such as pitting, rust, discoloration, and material loss. The tool uses for visual inspection is magnifying glasses, borescopes, and cameras can enhance the inspection process. The advantage of visual inspection is quick and cost-effective for detecting obvious signs of corrosion. The limitations of visual inspection is may not detect hidden or internal corrosion. Number 2 of inspection methods is nondestructive testing or NDT. Ultrasonic testing uses high-frequency sound waves to detect internal corrosion and material loss. It is effective for identifying wall thinning and internal defects. Radiographic testing employs X-rays or gamma rays to create images of the internal structure, revealing corrosion damage without damaging the material. Magnetic flux leakage detects corrosion in ferromagnetic materials by measuring changes in magnetic fields. The advantages of nondestructive testing is: provides detailed information about internal corrosion without damaging the material. The limitation of nondestructive testing is: requires specialized equipment and trained personnel. Number 3 of inspection methods is electrochemical techniques. Electrochemical impedance spectroscopy, or EIS, measures the impedance of a metal surface to detect corrosion rates. It provides detailed information about the electrochemical processes occurring on the metal surface. Linear polarization resistance, or LPR, determines the corrosion rate by measuring the polarization resistance of the metal. It is useful for real-time monitoring of corrosion rates. The advantages of electrochemical techniques is: provides quantitative data on corrosion rates and mechanisms. The limitation of electrochemical techniques is: requires specialized equipment and expertise. The second is monitoring methods. Number 1 of monitoring methods is corrosion coupons. Description of corrosion coupons is: metal samples placed in the environment to measure the rate of corrosion over time. Coupons are periodically removed and analyzed for weight loss and corrosion damage. Usage of corrosion coupons is: coupons are periodically removed and analyzed for weight loss and corrosion damage. The advantages of corrosion coupons is: simple and cost-effective method for monitoring corrosion rates. The limitation of corrosion coupons is: provides average corrosion rates over the exposure period and may not detect short-term corrosion events. Number 2 of monitoring methods is electrical resistance probes. Description of electrical resistance probes is probes that measure changes in electrical resistance as the metal corrodes. The resistance change is proportional to the amount of metal loss. The usage of electrical resistance probes is: provides continuous monitoring of corrosion rates. The advantages of electrical resistance probes is: provides continuous monitoring of corrosion rates. The limitation of electrical resistance probes is: requires calibration and may be affected by temperature changes. Thank you.